Hello everyone, this is John Hashmat and welcome to Physics Simply. In this video I will be solving the paper 4 exam for February-March 2025. But first, if you need a crash course or a final revision video for the whole syllabus, I have a link in the description and at the end of this video for a playlist which contains an entire fast track explanation of the whole syllabus for 0625 or 0972 syllabus for IGCSE. Now let's get started. Question 1 says figure 1.1 shows a force extension graph of a spring. We have the force in newtons and the extension in meters, and there are some negative values for a spring. When there is a negative force and negative extension, that means a compression. So a spring can have an original length, and you can either extend that length or decrease the length using a tension force or a compressive force. Now part A says calculate the spring constant of the spring. The spring constant is equal to the force divided by the extension from Hooke's law, F equals kx. Now we need to choose a suitable point from the graph. For example, I'm going to use this one. We have 2000 newtons on the y-axis and 0.04 meters on the x-axis. So we divide 2000 by 0.04. That gives an answer of 50,000, and the unit is Newton per meter according to the axis of the graph. Part B says a student states that the spring has not reached the limit of proportionality when the force is 4,500 newtons is applied to it. State how the graph shows that this statement is true. So a limit of proportionality is the end of the straight line, but at 4,500 newtons the graph still goes as a straight line. It has not curved yet. It usually curves towards the extension axis. So here the extension is on the x-axis, so it would curve to the right. If the extension was on the y-axis, it would curve upwards. Now we say that the graph is still a straight line. That is why it is considered to not have passed the limit of proportionality. Part C says springs can be compressed by forces. The spring described by figure 1.1 is compressed by a force F and has an extension of 0.025 meters. And we need to determine that force that gives this extension or its compression now. We can either use a graph or use the value of k we got from the last question. If we use the k, F equals kx, we have 50,000, and we multiply that by the force negative 0.025. That gives an answer of 1,250 newtons, and the same answer could be given from the graph directly. So we have 0.025, that is about here. So we go to the graph and then we see which force that gives on the y-axis. So we have this is 1,000 and this is 2,000 in negative. So each division here is 100, 1,100, 1,200, 1,300. So it's exactly in the middle between 1,200 and 1,300. So it's 1,250, just as we got it from the calculation here. Part D says state whether the force is a scalar quantity or a vector quantity. It is a vector quantity since it has direction. Scalar quantities do not have direction. Question 2 says trolley A and trolley B are on a horizontal frictionless bench. Trolley A moves to the right with a constant velocity u equals 0.44 meters per second. Trolley B is stationary. Figure 2.1 shows trolley A before it collides with trolley B, and the direction of motion is to the right and B is at rest. State the momentum before the collision for trolley B and explain your answer. So for anything that is at rest, the momentum is 0. And the explanation is momentum equals mass times velocity. And here the velocity is equal to 0. So the momentum is equal to 0. Part B says after the collision, the two trolleys are joined together and travel with a constant velocity v of 0.18 meters per second to the right. The mass of trolley A is 0.75 kilograms. So whenever we have two objects colliding, we use the law of conservation of momentum. And we need here to calculate the mass of trolley B. So the law of conservation of momentum is ma ua plus mb ub instead of 1 and 2 equals ma va plus mb vb. And then we substitute. The mass of A was 0.75 kilograms and its velocity before the collision is 0.44. And the momentum of B was 0 before the collision. After the collision, we have a mass of 0.75 for A with a known velocity of 0.18 plus the mass of B, which is unknown, multiplied by the same velocity 0.18. Or we can say that the total mass of 0.75 plus mb multiplied by 0.18 as a final momentum. Now we divide by 0.18 on the left side and then we subtract by 0.75, so the total calculation would be 0.75 times 0.44 divided by 0.18, and whatever that gives, we subtract 0.75. This gives an answer of 1.083 recurring, so we can approximate that to 1.08 or 1.1 kilogram. Part CI says the trolleys move onto a rough surface which exerts a constant force F on the trolleys and brings them to rest in 2.6 seconds. Calculate the force F. We can use force is equal to the rate of change of momentum, so mass multiplied by change in velocity over time, or mass times acceleration. We have the total mass of the trolleys 0.75 and 1.08, or the answer from the calculator. Multiplied by the change in velocity, the final is 0, the initial is 0.18, and the total time was given as 2.6. This gives an answer of negative 0.126923. We can approximate that to 0.127 or 0.13. According to the significant figures of the question, we have two significant figures. We can add one more significant figure here, and the unit for force is newtons. And we can write down the negative or leave it. It's not specified in this question. Double I says a different rough surface exerts a smaller resistive force on the trolleys. State how this affects the time taken to bring the trolleys to rest. Explain your answer. So for a less force or a lower force, we will take longer time. And the explanation is that we have less deceleration, because deceleration or acceleration is directly proportional to the resultant force. Or we can say that there is less rate of change of momentum, which is the definition of force. Question 3 says figure 3.1 shows a mains electric heater used to heat a small room. State the region of electromagnetic spectrum which radiates thermal energy. That would be infrared radiation. Part B says explain why the shiny metal surface behind the heating element increases the thermal energy radiated into the room. So basically radiation goes in every direction, including towards the backwards of the heating element. So that would be absorbed by the body of the heater, but that would be energy lost and not heating the room. So the reflecting surface here reflects the heat back into the room, so less energy is absorbed by the heater body itself. So this is what we are going to write here. Shiny surfaces are good reflectors of infrared radiation, so less heat is absorbed by the body of the heater itself, so less energy losses. Part C says the metal outer casing of the heater is earth. State why this is an important safety feature. The earth wire is supposed to prevent electric shocks, so to avoid electric shock. And the explanation of this is that if the live wire touches the casing, current will flow to earth instead of a person holding the casing. Part D says the mains voltage is 230 volts. The two identical heating elements are connected in parallel. Each heating element has a resistance of 89 ohms. Calculate the current in one heating element. So for in parallel connection, we have the same voltage, 230 volts, and each one of them has a resistance of 89 ohms. And we can calculate current as potential difference over resistance or voltage over resistance. So 230 divided by 89. That gives an answer of 2.58426 and so on. We can approximate that to two significant figures here according to the numbers in the question, or we can add one more significant figure, so 2.6 or 2.58 amperes. Double I says show that the electrical power of the heater as a whole, which means the two elements are working now, is approximately 1200 watts. State any equation you use in words or symbols. Just in case we got the current wrong, I'm gonna use the equation for power equals V squared over R. So we're gonna use the total voltage 230, that is squared, and the total resistance of the two components connected in parallel. We can use product over sum. So 89 multiplied by 89, R1 times R2 over 89 plus 89, R1 plus R2 to get the total resistance. You can calculate the resistance first, then use the equation, or write this whole thing on the calculator at once. That gives an answer of 1188, which is approximately 1200. Triple I says the heater is 95% efficient at converting electrical work done to thermal energy. Calculate the thermal energy emitted by the heater, which is the output energy, in DII in 60 seconds, and give your answer to two significant figures. So the equation for efficiency, it is the output over the input, but if we are going to use energy output, we must use energy input and then multiply by 100 to get a percentage. In this, we have the 95 as efficiency, 100 is given, and we need to calculate the energy output, but we don't have the energy input. We have the power input given as 1200, but we can use the equation for power equals energy divided by time, so we multiply time by power to get the energy here. So we multiply power by the time, which is 60 seconds, to get the energy. And then we need to make the energy output as subject to formula. So we multiply by this bracket and then we divide by 100. So we have 95 times 1200 times 60, and then we divide by 100 to get the answer, which is 6.84 times 10 to the power of 4 joules. Or we can approximate it to 6.8 times 10 to the power of 4 joules. Question 4 says a train has a maximum speed of 200 kilometers per hour. It accelerates from rest with constant acceleration of 0.70 meters per second squared. First, it requires the definition for acceleration. We say that it is the rate of change of velocity or the change in velocity per unit time. Double I says show that the maximum speed of the train is approximately 56 meters per second, and it also mentions at the top of the question that there is a maximum speed of 200 kilometers per hour, but now we require it in meters per second, so we convert the units. So speed equals distance over time. 200 kilometers means 1000 meters, so we multiply by 10 to the power of 3, and then dividing by the time, which is 1 hour per hour. So that's 1 hour. Converting it to seconds, we multiply by 60 minutes and 60 seconds. That gives an answer of 55.5 recurring, which is approximately 56 meters per second. Triple I says calculate the time taken for the train to reach its maximum speed. We have the initial velocity 0 and the final velocity equal to 56 meters per second, and the acceleration was given at the start of the question as 0.70, and we need the time, so we can use acceleration is equal to v minus u over t, or t equals v minus u over a, and then substitute 56 minus 0 over the acceleration 0.70. That gives an answer of 80 seconds. Part BI says the train has a total mass of 440,000 kilograms. Calculate the force which causes the acceleration of the train. So we use F equals ma. The mass is 440,000 and we multiply that by 0.70. That gives an answer of 308,000. We can write it in standard form, 3.08 times 10 to the power of 5 newtons, or 3.1 times 10 to the power of 5 newtons. Double I says the train travels into a headwind, which means there is a wind now pointing towards the head of the train, so it is opposite to the motion of the train. State and explain the effect of this force on the motion of the train. So we say that speed decreases, and the explanation is since there is now a force opposing the motion, now the acceleration decreases, or it might be even decelerating, but it's not specified here in the question. So we say that acceleration decreases, or we say that the separate force opposing the motion causes acceleration opposite to the motion. Question 5 says a light-dependent resistor has a low resistance in high light intensity and a high resistance in the dark. Sketch a graph of resistance against light intensity for an LDR. So we have the axis for a graph like this. But for an inverse relation, we draw a curved line with negative gradient and decreasing gradient like this, and then we label the axes. We have here resistance and intensity of light. You must remember that an inverse relation is always shaped like this, not a straight line. Part B says figure 5.1 shows part of the electric circuit used to turn on a light when it is dark. Complete the circuit in figure 5.1 with a symbol for a light-dependent resistor. So we have an empty space here. We draw a rectangle, which is a symbol for a resistor, but for an LDR, we draw two arrows pointing towards the rectangle. Double I says explain why the lamp is off in the light and the lamp is on in the dark. Use ideas about potential difference in your answer. So now for this type of connection, this is a potential divider circuit. So if the resistance on the bottom here decreases, the voltage also decreases. And since the lamp is connected in parallel with the LDR, its voltage also decreases because in parallel we have the same voltage. And when voltage on the lower connection is decreased, the voltage at the upper connection is increased, since these are in series with the battery and the battery has a full voltage which is constant. So if one voltage across one component increases, the other must decrease, so the total voltage remains constant. And in series always the voltage is proportional to resistance. So here, if the light intensity increases, the resistance of the LDR, or we say that if light decreases, the resistance of the LDR increases, and so does its voltage. So we can write either way. So if we start by saying if light intensity increases, the resistance of the LDR decreases, so the potential difference across it and across the lamp in parallel decreases, so there is low current in the lamp, and that low current may not be enough to light the lamp. Or we can rewrite this as vice versa. If light intensity decreases, the resistance of the LDR increases, so the potential difference across it and across the lamp in parallel increases, and now there is high current in the lamp because the voltage is high on the lamp. Question 6 says figure 6.1 shows an object O which is 5 centimeters away from the center of a thin converging lens called L. The focal length L is 3.0 centimeters. Figure 6.1 is drawn to full scale. Part A says on figure 6.1 label the principal axis with a P and find the place of the focal point and label it with the letter X. So we have here the principal axis is always perpendicular to the central line of the lens. So this is the principal axis, and we use a ruler to measure the distance. So we have 3 centimeters either side. So this is the object at a distance of 5 centimeters. We measure 3 centimeters from either side. So this could be a focal point X, or on the other side we can measure 3 centimeters and this point can be also labeled X as the focal point. Triple I says on figure 6.1 draw 2 rays from O to locate the tip of the image produced by the lens. So we can draw the first ray which is directed towards the optical center and does not bend. So we just draw a straight line from the tip of the object directed towards the optical center, which is the exact center of the lens. We have to make sure that it is exactly passing through the center and no bending, just draw a straight line using your ruler through the center of the lens. The other ray we draw, which is parallel to the principal axis, so a horizontal line since the principal axis is horizontal, and then bends towards one of the focal points, which is on the other side of the lens. So just to make sure that the line is horizontal perfectly, I'm going to measure the height of the object using my ruler here. So this is approximately, it's between 2.3 and 2.4 centimeters. So I'm gonna measure that the same here and mark the point. And then I'm joining the 2 points, the top of the object and that point I've marked at the center of the lens. And from the center of the lens, we go towards the focal point and extend the line. So using a ruler, we extend the line passing through the focal point and extend it forward like this. And this intersection point is the tip of the image. And by the way, the image would be shaped a triangle like the object, but pointing downwards. Its sharp edge would be pointing downwards, and the base would still be at the principal axis. So this is an inverted image. And we draw the arrows to identify the direction of motion of light. So the rays came out of the object and go towards the image. Part IV says in table 6.1, place a tick in the right-hand column next to all terms that describe the image in AIII. So the size of the image here is larger than the object. So this height is greater than that height, which is the object. So it is enlarged and the image would be pointing downward. So it is inverted and it is made of real intersection of rays, not extensions of rays. So this is a real image, not a virtual image. So we have enlarged, inverted, and real. Part B says the object moves closer to L. The new distance between L and the object is less than the focal length. Describe how the new image is different from the image in AIV. So we have the lens here. For a converging lens, if you place an object closer than the focal length, the object will create diverging rays. So the rays would be like this, and you would have to extend the rays backwards. So extensions of rays, that means virtual image, and the image will always be enlarged and upright. So the image in the first section of this question was enlarged, inverted, and real. Here the difference is that it is virtual now and it's upright, not inverted, but it is still enlarged. So the difference here is that the image will be upright and virtual instead of inverted and real. Question 7a says figure 7.1 is a scale drawing of light waves approaching a narrow slit. The scale here is 1 centimeter, represents 4.0 times 10 to the power negative 7 meters. And we have the wave fronts, 3 wave fronts, and a barrier with a gap in the middle. Name the wave effect produced by the narrow slit. So when waves move through a slit or around a corner, they spread out, and that is called diffraction. So this effect would be diffraction. Double I says, using figure 7.1, determine the wavelength of light and give your answer to 2 significant figures. So since the diagram is drawn to scale, we just measure the distance between 2 wavefronts. So using a ruler here, the distance is approximately 1.2 centimeters, and each centimeter was equal to 4 times 10 to the power negative 7 meters. So we use cross multiplication. If 1 centimeter represents 4 times 10 to the power negative 7, 1.1 centimeters would represent what? So we multiply 1.1 times 4 times 10 to the power negative 7, then we divide by 1. That gives an answer of 4.8 times 10 to the power of negative 7 meters. Triple I says on figure 7.1, draw 3 wavefronts that have passed through the narrow slit. The first thing we need to do is to draw a line that passes through the center of the slit or the gap here to represent the direction of the wave. And on that line, we draw equally spaced dots to represent the positions of the wavefronts. So we already measured the distance between 2 wavefronts as 1.2. So every 1.2 centimeters, we draw a point, but this had not yet passed the barrier. We move it again. We have a point at 1.2, 2.4, and 3.6. So 1.2 centimeter, 1.2, 1.2, 1.2, and so on. And since the gap here is narrow, we draw circular diffraction or curved diffraction using a compass. So using a compass here, I stand at the last wavefront which did not pass through the barrier, and then draw curved lines at the points specified. So this is the first curved line, like this. And the diagram is usually like a Wi-Fi signal. So we increase the width or the length of the curve. Then we extend to the last one, and we draw the last curve wider, like this. And this is our diffraction diagram. You can either leave this line, the horizontal line, or erase it or draw it as a dashed line. It's up to you. But there was a wavefront here in the middle of the gap, so we draw that one as a straight line. It did not pass the gap or the barrier. So we have the distance between wavefronts is the wavelength between a crest and the next crest. So we have one wavefront or one wavelength from here to here, one wavelength from here to here, here to here, and here to here. Part B says foghorn emits a sound with frequency 380 Hz. The sound is heard by a ship 2.5 kilometers away. From the foghorn, the speed of sound in air is 330 meters per second. Show that the wavelength of the sound is approximately 0.9 meters and state any equation you use. We're going to use the equation of speed. Speed is equal to wavelength multiplied by frequency. So the wavelength is equal to speed divided by frequency. We have speed 330 and we divide that by the frequency 380. That gives an answer of 0.868, which is approximately 0.9 meters. Now we need to calculate the time it takes for the sound to travel to the ship. From the foghorn, we have the distance and we have the speed, and waves travel with constant speed in a constant medium. So time is equal to distance divided by speed, and we have the distance in kilometers and the speed in meters per second. So we convert the kilometer into meters by multiplying by 1000, and then we divide by the speed 330. That gives an answer of 7.5757 and so on, recurring. So we can approximate that to 7.6 seconds. Question 8 says, figure 8.1 shows a metal rod suspended in the magnetic field produced by a pair of permanent magnets. The metal rod is connected to a cell and there is a current in the metal rod. State the direction of the force on the metal rod due to the current. So since there is already current in between the magnets, we use Fleming's left-hand rule to get the direction of the motion or the force. But first we need to decide on the directions of the magnetic field and the current in the rod. So current goes out of the positive terminal, which is a long line here. So going in this direction and pointing inclined upwards, that means into the page. And the magnetic field points from the north pole to the south pole, so the magnetic field is to the right. Now using Fleming's left-hand rule, the index finger points toward the direction of the magnetic field. The current is into the page using the middle finger. And now we have the thumb pointing downwards. So this is the answer, downwards. And the explanation is explaining how we used Fleming's left-hand rule. So first we say using Fleming's left-hand rule, index finger to the right, that's magnetic field, middle finger or second finger into page, that is the current. And now we have the thumb downwards. We already said that this is the force direction. Part B says the connections to the cell are reversed, which means the current will be reversed. State how this change affects the force on the metal rod, so the direction will be reversed, because reversing the current reverses the force, and reversing the magnetic field also reverses the force. But if you reverse both, you will get the same direction of the force. Part C says two magnets and the cell are used to make a simple electric motor as shown in figure 8.2. Describe the function of parts J, K, and M and L. So J first, this is a brush which is used to connect the battery or the cell here to the coil. Part K is the actual coil. So we have the coil, it rotates due to the current and the magnetic field. That is because the coil will have one force pointing in one direction and another force pointing in the other direction. And these forces are called a couple, and they cause a turning effect, which is called a torque or a moment. Now part L is just an axle to hold the coil in place instead of just falling down. So this is an axle to support the coil or hold it in place. And the last part, M, is a split ring or a commutator, which reverses the current in the coil every half cycle to make sure that the rotation is in the same direction or continuous rotation. Because if the coil is flat like this, one side would be going up, the other side would be going down. That's a clockwise rotation. But when the flat coil turns to the other side, for example, if we call these A, B, C, and D, AB is now moving up. After 180 degrees, we need AB to be going down to still be going in the same direction. And to reverse the force on AB, we have to reverse the current in the coil. And the same would go for CD. CD was going down, now it would be going up. Question 9 says, strontium-90 is a radioactive isotope of strontium. The nuclide notation for strontium-90 is 90 and 38. Explain what is meant by isotopes. These are atoms or nuclides of the same element, having same proton number, but different nucleon or neutron number. So the proton number decides whether I'm the same element or not. If you have the same proton number, you have the same element. Double I says complete table 9.1 for strontium-90. We have the name of the particle and the number of the particles and the location. Is it outside the nucleus or inside the nucleus? The only type of particle that is outside the nucleus is the electron. So we have the last one is proton inside the nucleus, and the neutron is also inside the nucleus. And we have the nucleon number here 90 and the proton number is 38. So if we need to get the neutron number, we subtract 38 from 90. That gives an answer of 52 protons. Part B says strontium-90 is used to measure the thickness of metal sheets in industry. Strontium-90 decays by beta emission, which passes through a metal sheet to a detector. So we have a source of radiation here that emits beta particles, and we have a thick sheet or thin sheet of a metal and a detector on the other side, and it detects the amount of beta particles that can go through the sheet. Part I says one metal sheet is 0.75 millimeters thick. Suggest why strontium-90 is a suitable radioactive source to measure the thickness of the metal sheets. So we say that beta particles can penetrate through a thin sheet, but as thickness increases, the number of beta particles penetrating decreases. Double I says the half-life of strontium-90 is approximately 27 years. Figure 9.1 shows the shape of a decay curve. The strontium-90 source is replaced with a new source after 15 years. Using figure 9.1 suggests why a strontium-90 source that is more than 15 years old needs to be replaced with a new source. So if we go to 15 here, the radiation is less than 3/4 of its initial value. So that could cause a misconception of the thickness of the metal sheet. Usually when less number of beta particles can pass through, that means that the thickness of the sheet is greater than usual. But now it is just due to the source losing most of its nuclides that are emitting beta particles, not due to the thickness of the sheet. So we say that the activity will be significantly less, which leads to incorrect thickness measurement. So we write our conclusion or our understanding of the question that makes us decide what to write in this type of question. So it is always related to the story of the question. Here's the story of the question, that we use the radiation to measure the thickness. So in this case, why do we need to replace a radioactive source after a certain amount of time? Because we are dependent on the number of radiation reached or detected by the detector. So if the number decreases for another reason other than the thickness of the sheet, now we are measuring incorrect measurements. Question 10 says figure 10.1 shows the path of the Earth as it orbits the Sun. X is the position on the Earth where scientists observe the apparent motion of the Sun throughout the year. Determine how many days it takes the Earth to move around its orbit from F to G. So F to G, that is quarter of a cycle. So we divide 365 days by 4. That gives an approximate value of 91.3 days. And the explanation here is that it is a quarter of a year, of a full year, which is the orbit around the Sun. Part B says figure 10.1 shows 4 positions E, F, G, and H of the Earth in its orbit on the Sun. Identify the position of the Earth when it is summer at X and winter at X. Now we have to notice the axis of the Earth, and X is in the upper hemisphere. So this is pointing toward the Sun now, and at H it's pointing away from the Sun. So this is summer and this is winter. Position E and G are called the equinoxes, which is points where the amount of time spent in daylight is equal to the amount of time spent in nighttime or away from the Sun. But for the positions F and H, F, the point X would be pointing towards the Sun most of the time, and at H it would be pointing away from the Sun most of the time. So summer was at F and winter was at H. Part C says the orbit speed of the Earth around the Sun is approximately 3 times 10 to the power of 4 meters per second. Calculate the average radius of the Earth's orbit. So the speed of the orbit, speed is equal to distance divided by time, but the distance here is the circumference of the circular orbit or the approximate circular orbit. So 2 pi r divided by the periodic time of the orbit. And we need to calculate the radius, so multiplying by t and dividing by 2 pi. And the speed here is in meters per second. We have 3 times 10 to the power of 4 multiplied by the time in seconds. So we have 365 days to complete an orbit around the Sun for Earth, multiplied by 24 hours, 60 minutes, and 60 seconds. Then we divide that by 2 pi. We get an approximate answer of 1.51 times 10 to the power of 11 meters. Pardis says Earth is a planet in the solar system. State one other type of a naturally occurring object that is present in the solar system. So we can say asteroids, dwarf planets, comet, or moons. So either one of these. And this was the end of the exam. I hope you enjoyed that video and found it useful to you. And again, if you need a crash course or a revision course, I have the link in the description of the video and in the click button right here. Keep practicing and I will see you in another video.